So let's start. Hi, I'm Erdian and I am representative of Polish team and I'm going to show you particle detector for dummies. First of all, I'm going to read the current the content of the problem. The problem was to build a simple device that can detect the cosmic ray particle, characterize the particle identification capabilities of your device, try to test your device in different conditions, and also try to obtain the energy spectrum of the cosmic ray particles. Okay. The main source of the cosmic radiation are from the center of our galaxy and the sun. And in the picture, most of the radiation are high energy protons. It's about 90% of radiation, and the protons can collide with atmospheric molecules and create another particles, especially the pions. Charged pions decay to the muons and neutrinos. The products of this collide we call the cosmic shower. In the picture we can see the vertical flux of cosmic shower depends of the altitude. And in the level of C, 71% of cosmic shower are muons, 28% of cosmic shower is electrons, and 1% nucleons. Okay, so charged particles lose the energy during the propagation through matter. Mean energy losses per unit distance are described by the Bethe-Bloch formula. This energy losses can be used to detect the particles. There are many types of particle detectors making use of this effect. For example, scintillating counter, semiconductor detectors, or gas detectors. And now I'm going to tell something about the gas detectors. In this graph we can see the dependence of charge collected in the gas detector, independence of voltage applied. As we can see, there are three regions of the work of such a detectors. First region is ion chamber region, and the second proportional counting region, and the third Geiger region. In the proportional region, Okay, so maybe I will tell something about Geiger-Müller tube. The Geiger-Müller tube is built with anode wire what is inside the Geiger tube and the tube wall. To anode wire we applied high positive voltage. When the particle Okay.
When the particle enters the Geiger mirror tube, it can cause the ionization of the gas inside. The gas is then accelerated by the voltage and hits in other molecules, causing avalanches of ionization, which can be collected and measured as a current on Geiger mirror tube. So we propose our design is gas chamber detector working in the Geiger region. We decide to utilize commercial Geiger tubes. Basically, we have one commercial Geiger tube and one old Geiger tube made in this country, which I found on my attic. It was made a lot of time ago. Geiger tubes are easily available in Poland, as I said, in the store or as old memories just fixed. Simple electronic circuit was we built simple electronic circuits that allow us to make a readout of the Geiger tube. This simple device gives us the possibility to detect charged particles coming from the cosmic rays, neutral radioactivity, and calibration sources. So, as you can see on the scheme, it consists of the shunt resistor, high-pass filter, and Geiger tube, and to Geiger tube there is applied high voltage. So, to distinguish cosmic rays from the other sources of charged particles, we decided to arrange two Geiger tubes with our custom readout in a coincidence mode. In such mode, only having signals on both detectors at the same time gives us a valid signal of presence of a cosmic ray. The other events are discarded and may put into erasure. Introducing absorber plate between the tubes guarantees suppression of a background coming from the low energy particle from other sources that can possibly generate coincidence. For example, it could be natural radiation of radon or radiation of some isotopes from walls, and so on. So our device looks like that. There is no plate in this photo because the final photo sadly was corrupted. As you can see, it is a very simple circuit. Now we plug it into oscilloscope and we put it in a trigger mode for one of the channels for the Geiger tube, which response was higher, and all we have done to obtain our measurements was only to calculate the number of events per time. So, measurements. During 20 minutes of measurements, we have detected 18 coincidences between channel 1 and channel 2, which means we have 0.9 plus minus 0.2 coincidence for 1 minute, and the uncertainties are taken from the Poissonian distribution second moment minus, Our Geiger tubes had active surface equal to about 7 centimeters squared. Cosmic flux level in the level of the sea is equal this amount, and when we recalculate and compare it with our setup, this means that efficiency of our detector is about 13%. So there's one more thing. This setup does not does not make the difference between the different energy particles, but if we have better tubes or tubes with the higher active surface, we could use them in a proportionality mode. But sadly our tubes wasn't good enough, and we thought that the dummies word meant that we couldn't just buy the very good ones. So thank you for your attention.
Okay, so sorry for the technical problem, maybe you can fix it while I'm talking. So I'm Anthony from École Polytechnique, and I will report problem number 12 oppose problem number 12 particle detector for dummies. So first of all, thank you for this presentation. It was very clear and the setup was quite great, so thank you. For reminders, can you go to slide 2? For reminders, the problem wanted us to create a simple, the most simple cosmic ray detector able to identify some cosmic ray particles and also to measure energy of them. So for the summary of the presentation, first theoretically you made a good point by explaining what are cosmic rays. Then you showed us some things about the energy deposition in matter, which is a very key factor to build detectors, in fact. To build particle detectors. And you also then told us about the theory of gas detector and most importantly Geiger-Müller tubes. So and then you explained that this is the device you actually built. So you showed us your experiments and explained further explained them further. You also told us that you used a coincidence detection to be sure you measure cosmic ray particles. And then you showed us a very great measure of the flux of muons at ground level with your detector and assessed the efficiency of your detector with that measurement. So now for the good points, I think you answered to the problem because you made a simple detector, which is a Geiger tube. You also quantified its efficiency. You use coincidence detection to be sure that you detect cosmic rays. So this is a kind of particle identification capability of your device. Then you talked theoretically about energy deposition in matter for particles, which can be used to assess energy spectrum, but you weren't able to measure them because your device is maybe too simple or you didn't have enough time to investigate further. For using your device in different conditions, I don't think you made it. You used plates to isolate it from the outside, and
no, we used plates.
sorry, I understood you made plates to isolate it from radiation, but you didn't tell about different conditions. So now there are a few points I want to discuss. First, can you explain a little bit further what is coincidence detection? And because you were really fast on that, and I think there are maybe some people didn't understand it. Then I would like to know if you have any idea to simplify your device further, but it's really nice and really simple already. Then you presented several gas detection. You talked about several gas detection detector. Why did you choose Geiger-Müller ones and why not the others? Then I think I didn't really understand what is the role of the plate or that thing, so maybe you can answer that. Well, and for further discussion, maybe we can talk about phenomena and further improvements of your device. We could talk about where the cosmic rays come from, but it's a little bit too far. Most importantly, I would like to know if you have any other idea to make energy measurements with your device without make it more complicated than it is now. So I think we can start by explaining me what is coincidence detection in a few words.
Yes. Can you, Pavel, put our computer? Can we change the?
Yes.
So I will briefly start.
Maybe you can
when the particle arrives at the Geiger-Müller tube, it causes this avalanche, which can we measure on our high-pass filter, as was in the scheme. Click.
Which slide?
Can you click so I can change it? The scheme with the high-pass filter. Okay, I can use. It's all right.
Okay.
This flow current can be measured on a high-pass filter, on the resistor on the high-pass filter, as voltage. If we use only one Geiger tube, we couldn't distinguish from where these particles came from. If we use two Geiger mirror tubes, we only counted the particles that when you from other side, which crossed both of it. So they have to arrive from the upwards, and most of the cosmic radiation comes from that direction, because from the other ones
the word coincidence means that there are two things happening nearly at the same time.
Yes.
So, in a few words, what are coincidence detection?
Okay.
What's the point of coincidence detection?
On
that's the
oscilloscope,
point.
we've got the signal from both the Geiger tubes, and when we got the signal from both of it in our oscilloscope, you can tell that the particle came through both of Geiger tubes
At the same time, because
at the same time.
So you are telling me that you measure speed of particle between your tubes.
No.
No. We use this coincidence to difference from, for example, black currents or false positives.
Okay.
Because it pushes the probability of false positives into the next order.
No. Okay. So what I think you're doing is you are taking these two signals, and when do you count a detection?
We count detection when the signal is. This is the example of a count. When we count signal as a valid detection if the signal was on both of the Geiger tubes at the nearly same time.
At the nearly same time. Okay.
Yes.
What time?
As you can see, on a time scale of 50 microseconds.
It's like indistinguishable. Okay, so it's like nanoseconds. So you have your distance between your two
Yes.
detectors. You have you say that you count a measurement only when you have detections in a range of like nanoseconds. So you are measuring a speed, and in fact you are discriminating the particles with the speed they are having.
So we could make it if we have oscilloscope.
We will maybe discuss it later.
Okay.
But I think that's exactly what you did. Now, for another question that we can talk about, you said that you didn't measure the energy of the particle with your device because it would have taken you too far and complexify your device. I think there is some way to make an energy measurement without complexifying your device.
Yeah, I thought about it, that we could work instead of a Geiger regime, we could work in a proportionality regime. But the Geiger tubes used was in poor condition, and when the voltage dropped like below 250 volts, there was nearly no detections.
Okay. Do you know what happened to muons when they traveled through the atmosphere?
They, as you can see from this graph, they lose energy very slowly.
But,
so
yes.
they can
Are they stable?
No, muons are not.
But they got very large speed, so
in our reference frame, the time, the half time of light life is enough.
Do you know the proper lifetime of muons?
I can't tell from my head, but I know that
it's like 2.2 microseconds. Now, what I wanted to say is that if you use this decay time, you can measure energy by measuring flux of muons, because muons with grazing incidence, we have to travel a longer distance, and so they will have a more chance to decay depending on the energy. So maybe with your detector, if you put them apart, you can detect energy. Okay, so all right.
Okay. I'm Paul from Germany, and I'm going to hold a review of the presentations and the discussion held earlier. First, about the task, I think we've seen it enough. A few remarks about the reporter. They at first defined what they consider cosmic particles, namely muons, brought up the aspect of the Bethe-Bloch formula, and discussed their device, how they built it, and showed their measurement results. Unfortunately, a few points were missing, like a further discussion of the Bethe-Bloch formula or some calibrations, but that was already partially covered by the opponent. To talk about the opponent, one good thing I noted is that he criticized the non-simplicity of the device, because in some aspects, another positive thing was that you earlier mentioned 3 possible detection principles, but you did not discuss about why you chose the one you did.
I was during the...
Okay. A few negative things were that the slides weren't quite readable, and I think you mentioned the possibility of the energy measurement, but that is something we can talk about later a little. And one important additional thing was that the lack of any spectra or different plots were missing. The only result we got was one number with a calculated Poisson error. To summarize the discussion, it mainly revolved around the coincidence measurement, which is on one hand a good thing because it's a very vital part of the detector, but on the other hand, I think less time could have been spent talking about this topic. The lack of energy resolution was mentioned and briefly discussed, and as improvements were suggested. Okay. There are a few questions I want to bring up for the following discussion, namely typical energies for cosmic rays. These were not really discussed earlier, only briefly shown in the plot. What energies is your plate able to filter out? Can you distinguish particle type? And is it possible to obtain an energy spectrum? Okay. We can start the discussion. I think the energy spectrum is the first thing I want to talk about. Namely, I want to ask the opponent.
Okay.
You said earlier you think it's possible.
Yeah, okay.
How do you want to?
I don't know enough about Geiger tubes to know if it's possible to get the energy spectrum, but what I'm sure is that we can use this device to have a mean energy of muons. And also, if we obtain a spectrum, we would have to discuss if this is the real spectrum of muons or the spectrum of the energy deposition, which is not the same according to Hans Bethe formula. Okay.
What do you think about that?
And this question about spectrum is connected to the question about the different regimes. I thought we could improve it by measuring it in a regime of proportionality of the charge, but our tubes was not good enough, and when the voltage dropped below 250 volts, which is above the Geiger regime limit, we couldn't have any detections for some reason.
What do you think about that? That the proportional mode could be used if the...
I really don't know how Geiger tube works, so
Okay.
I can just know what they say, so I can tell them.
I'm pretty sure that if you plug in the numbers in the Bethe-Bloch formula, you obtain like 2 mega electron volts lost per centimeter of lead. In your Geiger tube there's air,
No,
meaning it's even
2
low.
mega electron volts multiplied by the density of lead divided by the distance you... It's 2 mega electron volts, and you have
Okay,
to
but
multiply
still
by the
it's
density.
way lower than the mean energy of a muon, meaning
Yes.
over the area of your Geiger counter there will be barely any energy loss and you won't be able to obtain any energy spectrum.
No.
this way.
There was no measurement on the plate. The plate was to, as you said, it is the mean loss of energy is much lower than the mean energy of the cosmic ray particles. So we want our detector to measure, to distinguish.
And you see, it's not so bad because with this plate, this detector is filtering background radiation,
what I
natural
thought,
radiation.
from radon and something like that, from unstable isotopes. So we know we measure only the high energy particles.
High energy.
Okay, so
Maybe we can switch to another topic.
Yes.
yes.
How did you define for your device simple? Because it's obviously possible to build more complicated devices, but you obviously had to make a cut. What is possible for you to allow on your device and what's impossible?
I think it's not exactly physics. It's just simple. It's
Yes.
simple. It has been done like centuries. No, not exactly a century, but I think simpler means that we can make it for less than say €100.
Yes.
$100 or 100.
Yes, for us, the main criteria for choosing how to build it was the price. We focused to lower the price as much as we can, because for example, this 300 volt supply is, we can show it, is just flying back supply. You know that
Okay.
that converts
That's
volt, yes.
a well enough
And it is very cheap because
definition,
we built
and
it.
it's good that the both of you can agree on that. Another question to the opponent. Do you think it would be possible to distinguish particle types? Like,
So that's what I wanted to point out with the explanation of coincidence detection. So
for teams to join.
So I continue to talk. Coincidence is that you are taking two detectors which are separated by a certain distance, and you know this distance, and then you know that cosmic rays are going like the speed of light. So you know exactly what time they should take to pass through the two detectors, and then using electronics like you did with the oscilloscopes, you can say that you have effectively a detection of a cosmic ray when you have two detections within a range of that time, which is like nanoseconds. The light travel 30 centimeters per nanosecond.
Not exactly, because
you
you don't know in which part of our Geiger tube the particles.
Yes, because your
and
Geiger tube is a volumic detector. You detect
Yes,
the volume.
and
But you could say it's a characteristic distance of like 1 centimeter. So it makes you distinguish particles which are. No, you can
1
separate
centimeter
your
is the
if you separate
distance
your-
between the center of Geiger tubes.
Okay.
Not
So
exactly.
you can do that, and it makes you distinguish between fast and slow particles. But identifying the mass and charge or things like that, it's much more complicated.
Yes,
Okay, I think-
but by your idea, we could only, if we have enough the temporal resolution, we could distinguish different speeds, not the energies, because we don't
But
know.
speeds
Okay,
are
I
related
think-
to energy.
Yes.
we should include the audience as
That
well,
is-
because there are
But
a few
there are.
Okay, I have a question to the reviewer, to opponent about this concept of detecting beyond energy by measuring the lifetime of something. Yes?
Okay, it's maybe quite long, so I don't know if I can present it.
Maybe if you can ask a concrete question about it, you can answer it shortly.
The idea is that the rate at which muon decays
Okay.
in their proper time is a constant, and it's known. And so the rate at which they decay in our frame of reference depends on their energy. And by doing experiments of anisotropy, that means what is the flux of muon which is vertical, and what is the flux of muon which is like coming from a grazing incidence, you can measure how many muons decay in a certain amount of time, and by that you can get an average energy.
Okay,
So
to
with
conclude,
two
you're
detectors, you
measuring the angle dependency, and from that one you can calculate the energy spectrum.
Exactly.
Okay, then let's go to a further question.
Okay, so in the problem it's stated to test the device under different conditions. What different conditions you think you could use, and what influence would they have?
We could measure, for example, the cosmic radiation at the sea level and also some top of the mountain, and for example in the basement.
Yeah, but what would you measure?
What
Yeah, what do you expect
we
from, for example,
also when you measure on a higher altitude, as we can see from the slide about the cosmic radiation energy distribution, there would be more counts per minute on the higher altitudes, and for example in the basement, when we are separated by some concrete few meters walls, there would be fewer counts.
Okay. Another question?
Why you're focusing on the Geiger tube, and which other devices are possible in your opinion?
For example, condensation chambers or condensation chambers is.
And then why you focus on the Geiger mirror?
For us, the Geiger mirror was the easiest and the cheapest to build because taking into account the average, for example, skills of an interested student from a high school.
Question to the opponent. Do you agree that the Geiger counter presents a simple, cheap solution in comparison to the other possibilities?
I agree. Well, I think cloud chambers are cheaper and easier detectors, but you cannot make real quantitative measurement with that. And to have quantitative measurement, I think Geiger tubes are the most simple devices. But I don't know many devices. I didn't know a lot about Geiger tubes before arriving here. So.
Okay, we have only 30 seconds left, so I'd like to conclude this discussion with a final question. Was there any particular reason why you chose 20 minutes as a measuring time?
I think that was. Yeah, no, there was no particular reason. We just measure it on like one sit and then we go to have something to eat. When we get angry, we stop measuring.
Can you detector while you are eating?